Hello students, today we are going to talk about the very famous experiment which proved that experimentally that a particle is possessing wave nature, which was predicted by de Broglie. Any moving particle is having wave nature, is having certain wavelength associated with it. That was proposed by de Broglie, and experimentally it was proved by the experiment of Davisson and Germer. Well, in this arrangement, what they did is they took a electron gun which produced monochromatic collimated electron beams, which were these electrons in the gun were accelerated through a potential difference of 54 volt and then filtered so that all the electrons were having same kinetic energy, and that these rays were incident on a nickel crystal having some scattering angle phi. The scattered rays were detected by a electron detector which was capable of moving on a circle, keeping the crystal at the center of that circle. And they found that for particular angle, scattering angle 50 degree, the intensity of scattered light was found to be maximum, and for all other angles this intensity was reduced. Corresponding to this scattering angle, the angle the beam makes with the surface of nickel is known as glancing angle. So they observed this, and according to de Broglie, the wavelength associated with the electron which is being accelerated through 54 degree or 54 volt will be given by the relation half mv square is equal to E into V. The potential energy converts into the kinetic energy, the maximum kinetic energy of the electrons, and from this the momentum of the electron can be calculated, and when feeding the momentum, that is this expression in the denominator, h divided by the momentum of the electrons gives us the de Broglie wavelength, and it can be calculated by putting the value of h, putting the value of mass of electron, charge on electron, and potential difference across which the electrons were accelerated. The wavelength associated with the electrons could be calculated. We have done it in the previous lecture and is found to be 1.67 angstrom. Now this was predicted by de Broglie. Now there is one law which is known as Bragg's law. What it says that when a beam of light is incident on a crystal, the diffraction pattern is formed, and the diffraction having the location where the maximum intensity is found is satisfying the relation 2d sin theta is equal to n lambda, where n is an integer. For maximum intensity we have n is equal to 1, and d is the lattice spacing between the two layers of the crystal, which is in this case for nickel we have 0.91 angstrom, and the angle, the glancing angle of in this experiment was for which they got the maximum intensity was 65 degree. So putting the value of theta 65 degree in this equation and taking n is equal to 1, the wavelength of this wave which was producing a diffraction pattern was found to be equal to 1.65 angstrom when we put this value of d theta and taking n is equal to 1. So these two values, wavelength predicted and wavelength found experimentally were found to be in very good agreement, and this proved that the de Broglie wavelength is associated with a moving electron, and this brought them Nobel Prize as well. Well, you see here you can find the path difference between these two rays, which is say let us call it ray 1 and ray 2. The path difference between ray 1 and ray 2 producing some diffraction pattern over here is nothing but C1B1 plus B1C. Now we have this angle theta, therefore the angle C1BB1 will be also theta and B1BC will also be theta. So from this right angle triangle BC1B1, where we have dropped a perpendicular on AB1 from point B, and that is BC1. So if you find the value of CB1, what you see is sin theta is equal to perpendicular, that is C1B1 divided by BB1, and BB1 is the lattice spacing. So we have sin theta is equal to C1B1 by D. That means C1B1 is equal to D sin theta. C1B1 is D sin theta, and in the same fashion you can find the value of B1C, which will be again D sin theta. So the total path difference between ray 1 and ray 2 will be D sin theta plus D sin theta becomes 2D sin theta. Now the interference, the diffraction pattern will have maximum intensity when the path difference between these two rays is such that it produces zero phase difference, and that will be the case only when the path difference is an integral multiple of wavelength, because if the path difference is equal to one wavelength, phase difference will be zero. If the path difference is equal to two wavelength, twice the wavelength, still the phase difference will be zero. So that means this condition will be satisfied for the maximum intensity of the diffraction pattern, and therefore they calculated the wavelength associated with this wave which was producing diffraction pattern, and that was found to be equal to the same and nearly same that which was predicted by de Broglie. So this brought a revolution, and in this process, while we have studied the topics in this chapter, we have now understood that wave behaves like a particle, and particle behaves like a moving particle behaves like a wave. When the photo emission took place, it was clearly seen that the momentum possessed by the wave was transferred to the electrons which jumped out from the metallic surface. So that means the wave was possessing the particle nature, and here we have proved that the particle is possessing the wave nature. So that's all for today. Thank you and have a nice day.